Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Good morning, students. We started isomerism in our last class, as you know. So, what is isomerism? The definition and the types of isomerism, those things we have already seen. So, the isomerism, if two different compounds have same molecular formula, then this phenomena is called isomerism. And the compounds which are having same molecular formula are called isomers. And there one example that we already see, and that there are two types of isomerism. One is the structural isomerism, another is we call the stereoisomerism. The structural isomerism, we know it is because of the difference in the structure, and the stereoisomerism is because of the difference in orientation of different groups to a particular carbon atom or maybe two carbon atoms that are part of the molecule. Then we have seen the structural isomerism, mostly of four different types. Chain isomerism. What is chain isomerism? In fact, we know the difference in the skeletal structure. The position isomerism, we'll see the certain substituents or maybe certain functional groups are at different positions in the same chain. The skeleton is same, but the positions of double bonds or maybe the certain functional group like ketonic carbonyl group or maybe some substituents like other functional group, halogens and other things are at different attached to different positions. So means at different carbon atoms in the numbering when you do the numbering of the carbon atoms. Then the functional group isomerism. Functional group isomerism different. They are having same molecular formula but different functional groups. The position isomerism we also saw that alcohols also show position isomer. All the halo compounds show position isomerism. Ketones show position isomerism. Double bonds, triple bonds show position isomerism. And a functional group isomerism that we know the aldehydes and ketones, they are functional isomers if they have same molecular formula. The alcohols and ethers, they are functional isomers if they have same molecular formula. Similarly, carboxylic acids and esters, they show functional isomerism if they have same molecular formula. The metamerism, we saw that around a particular functional group, the different alkyl groups which are connected to these functional groups are different. Usually, this kind of isomerism are shown by ethers, most common example. Then we also know about the amines, secondary, tertiary amines also show metamerism. The esters also show metamerism. These examples we have already seen. And then the tautomerism, that way one may call this as a structural isomerism, but this is actually the same molecule in different form, or means the same compound having two different structures, and that those structures are in equilibrium. That is why in your book this is not kept into the structural isomerism part, but some books refers it as a structural isomerism because the two compounds which are in equilibrium with each other, which are interconvertible, they are different compounds, their structures are different. And so the tautomerism we have also seen. Then we have also seen ring chain isomerism. The examples we have seen in electrocyclization, we see these kind of examples. Then the stereoisomerism. Today I will be focusing on stereoisomerism. And stereoisomerism, we have seen the same structural formula, same pattern of covalent bonding. But we see there is slight difference, or maybe one or two places difference in the attachment of the different groups at the carbon atoms. And because of that, the properties of two different compounds are different. Means these two compounds will be the same. All the atoms are same. Their structure, if you look at the covalent bonding pattern of covalent bonding, that is also same. But we see the orientation of different groups are different, and these stereoisomers are of two types: the geometrical isomers and the optical isomers. How the stereoisomerism is of the two different types: geometrical isomerism and optical isomerism. The one more thing I have said, the conformational isomerism. Sometimes some books refers for the conformers. They are conformers. They are not isomers. They are basically the different physical form of the same compound, and we can see this equilibrium maybe because of the change in the temperature or the thermal states. Now these things we have already seen, and I have also briefly explained everything. The tautomerism, different types of tautomerism. Now let's see the stereoisomerism. And the stereoisomerism today I will mostly focusing on geometrical isomerism, and in next class we will study optical isomerism. So the stereoisomerism, the compounds that have the same constitution and a sequence of covalent bonds. So they have same constitution and the same sequence of covalent bonds. It means they have same structure, but they differ in relative positions of their atoms of group in space. It means the relative positioning of the different group, or that we call the orientation, is different in the three-dimensional space or in the space, and that is why we see their properties. Some of their properties are different. They may have some common properties, but some of their properties are different. This type of isomerism is called stereoisomerism, and it can be classified, this stereoisomerism can be classified into geometrical and optical isomerism. Let us first focus on geometrical isomerism. So geometrical isomerism occurs due to restricted rotation of carbon-carbon double bond or single bond in cyclic compounds, or restricted. So what is important here is the restricted rotation of carbon-carbon double bonds. So this kind of isomerism we'll see only where there is a restricted rotation of carbon-carbon double bond, or maybe even if the single bond is there, but this that single bond is part of the cyclic compound. Then only we will have restricted or hindered rotation around a particular bond. Otherwise, all the single bonds, the single bond carbon-carbon single bond is there. They will freely rotate. They will freely change its physical positions of that we call also the a dihedral angle, and because of the change in the dihedral angle, there can have different conformers, and these conformers, their energies, they are also called rotamers. Those things we will see later on when we will study alkane, different types of rotamers or the conformers. So these conformers, their energy is not much different until unless for the simple organic compounds they are not much different until unless we go into very complex compounds like proteins, nucleic acids, and so on. So their conformers and their easily retrievable rotamers, their barrier is around 1 to 2 kilocalorie, below 2 kilocalorie per mole, and 2 kilocalorie per mole below this barrier. Up to this barrier is almost a barrierless process, so they can freely rotate around that single bond. However, if the compound is having restricted rotation means that particular bond is not freely rotatable. So it will not freely move this side to that side, and one part will not rotate with respect to the other part freely. So there is some restriction in this rotation, and that is we call the restricted rotation. And this restriction occurs whenever there is a double bond in the compound, or maybe there is a cyclic or the ring structure. So geometrical isomers are stereoisomers that differ in arrangement of groups with respect to double bond or ring structure. So if there is a double bond on the ring or the ring structure, means there is a restricted rotation about a carbon-carbon bond. That could be carbon-carbon double bond, or maybe the cyclic or the ring compound having this, if the single bond is part of the cyclic compound. And then the different groups, arrangement of different groups with respect to double bond or ring structure is different, then we see the geometrical isomerism. So two types of notifications are most commonly used to represent geometrical isomers. One we call cis trans notation, and another is EZ notation. Let's first focus on cis trans notation or cis trans representation. Let's first see this example: cis butene or cis but trans butene, or cis 2-butene trans 2-butene. So 2-butene is the one chemical compound that you know. So double bond is at the between second and third carbon, and so this is 2-butene. If these two CH3 groups are on the same side of the double bond, or maybe I can bring this CH3 group at this side or exchange this CH3 group with this hydrogen, their positions they can exchange. So I'll obtain this group here. Maybe we have exchanged this one. So what happens? So one can see these orientations are different, and these orientations, this is not freely convertible. So if once the CH3 group is attached in this form, this double bond is not freely rotatable. It to rotate this part of the compound with respect to this part, or maybe this part of the compound with respect to this part, you will have to break the pi bond first. And because of pi bond, why you have to break the pi bond? Because we have seen in the pi bonds there are overlap at above the internuclear axis and the below internuclear axis. So at the 2 points there is overlap, and if the overlap is at 2 different points, then such bonds are not freely. However, the sigma bonds we see overlap is along the internuclear axis, and even if the groups they can freely rotate, there is only 1 point of linking between two atoms in sigma bonds. However, in the pi bonds there are 2 points of linking. One may be the above internuclear axis, another is below internuclear axis, and this kind of things and the structures we have already seen in chemical bonding. If you don't remember, you can go and just watch that video, or maybe you can see those structures whatever I have shown. you earlier. So this double bond is if this bond. So if suppose from this structure I want to make this structure, then I'll have to first break this bond, and then I'll have to keep this portion fixed, and I'll have to rotate this portion, this one, and then only I'll get this structure. So to break, I'll have to first break the pi bond, and to break the pi bond, I need to provide certain energy. So there is no free rotation. There is certain energy penalty associated to this rotation, and so this kind of conversions are not free, and this kind of conversions are associated with certain high barrier. And so these both type of compounds that can exist in nature. So even one with this kind of linking of atoms of the groups, and another with this kind of linking of atoms or groups. And so these are, in this case, we call cis and trans isomers. This is 2-butene, and 2-butene exists in two different types of structure, and these are two we call cis isomer and trans isomer. If two CH3 groups, these CH3 groups, or the same groups, if the same groups are on the same side of the double bond, this is double bond, and both CH3 groups are on the same side of the double bond, then this we call as cis isomer. And if same groups are at opposite side of the double bond. This is the double bond, and the one CH3 group is on this side, another CH2 group is on this side of the double bond, one above on this in this structure, one above the double bond, one below the double bond. Since they are in the opposite sides, then this type of isomers are called trans isomers. So these are two isomers of 2-butene, cis isomers and trans isomers. Now, so let's see this kind of E and Z notations. I'll explain it in details later on, but in this example, because we have already mentioned EZ notations, we can see, let's see what are these. So these are two examples, and in these examples, what happens? We'll talk first in the kind of EZ notations. We try to find out groups with the higher priority and the lower priority. How will you find out the higher and lower priority groups that is connected to a carbon atom which is linked to the double bond, or so that there is a certain rule CAN in gold trilog rule, those that all the set of rules we will study later on. So suppose there are two groups that is connected to this carbon, and this one is having high priority, another is having low priority, and this similarly two groups are attached to this carbon having double bond. So this is high priority, this is low priority. A rough estimate to get the higher and lower priority group is which group is the bulkier. Usually the bulkier group gets higher priority than the smaller groups. Bulkier means the larger group gets higher priority than the lower groups. Means if there are atoms only, so you can see which atom is the larger, which is larger in size, or which atom is having higher atomic number or mass number. Then you can simply get the which group is larger in size, so which group will having higher priority. So this bromine is larger in size, so it will get higher priority than fluorine. In this case, as you know, the hydrogen is smaller, and this CH3 carbon is larger, and then it also is also having 3 hydrogen atoms. This is larger in size, so this will get higher priority. If the two higher priority groups are on the same side, then we call such isomers as a Z isomer. So this is Z isomer or the G isomer. And if these higher priority groups are on the opposite sides of the double bond, this double bond, same higher priority groups on the same side of the double bond, then it is Z isomer, and higher priority groups are on the opposite side of the double bond, then they are E isomers. So this we can also write the IUPAC nomenclature using this geometrical isomers, the notations that we use to represent geometrical isomers. So see, these are two different compounds. This compound is different, this compound is different, and they have a uh, some properties, some of their properties are the same, but most of their physical properties are different. So even also their chemical properties also differ to a certain extent. So these are different compounds. To differentiate between them, what we'll write, we'll write this cis, and the IUPAC name is butene. So cis butene or cis 2-butene, and this is trans 2-butene because we write this as in IUPAC nomenclature. Now this form the IUPAC nomenclature. If this compound was there, you can simply write. You can start the numbering from this carbon. So 1, 2, 3. So this is 1, 2, 3. This is a propene, and this propene, the double bond is at the first position, and there are two substituents, bromo and fluoro. So one can call one bromo, one fluoro, propene 1 or one propene. one bromo, one fluoro, one propene, or no, not one propene, because even if this double bond is here, there is no position isomer. So this is propene. One bromo, one fluoropropene. And this is Z isomer, so we'll write Z. Usually we keep this Z or E in parenthesis, inside the parenthesis. Now this is E, so that the compound is same, 1, 2, 3. This is one bromo, one fluoropropene, and this is E form of this compound, so this is E, one bromo, one fluoropropene. So this is the RQAC nomenclature we write for the symmetrical isomers. So the cis and trans isomers, let's now focus in more details on cis and trans isomers. The cis isomers, as we know, in this example, the two methyl groups are arranged on the same side of the double bond, whereas in the trans isomers, they are on the opposite side. The trans isomers, the CH3 groups, are on the opposite side. These forms are not interconvertible due to restricted rotations of the double bond. So this is very important point. These two forms are not easily interconvertible because there is a restricted rotation around this double bond. To interconvert, to get converted into one form to another bond, one has to first break this pi bond, and to break the pi bond, one has to provide lots of energy. Now let's see the example of cis and trans isomers in the form of the ring structure. So this is ring structure, one from 4-dimethyl cyclohexane. This is 1,4-dimethyl, you can see here, this is cyclohexane, and this is 1 and 4. First and fourth position, the two methyl groups are attached. So this is one from 4-dimethyl cyclohexane, and this is cis form because the CH3 groups are on the same side. However, as we know, the chair form is the most chair conformer of the cyclohexane is more stable. So let's see the same structure in the chair form. The chair form, as we know, in the chair form, there are two positions of the at the each corner. One is called the axial position, there is another one we call equatorial position. This is axial position. This group also will have this axial position and the equatorial position. Axial position, equatorial position. This will also have axial position and equatorial position. This axial position, equatorial position, axial position, and equatorial position. Now these groups are on the cis side and one at 1 and 4 positions. And what we know usually if the bulkier groups are there, it gets equatorial position, because when the groups are at the equatorial positions, there are lesser interactions or lesser uh, dihedral interaction. And because of the lesser dihedral interactions, the energy of such conformers are lower. So if the two CH3 groups are there, let's keep one CH3 group on the equatorial position, now another CH3 group. If another CH3 group I will keep at the fourth position, again at the equatorial position, it will go in this direction. And if it goes in this direction, this will be in the opposite side at 180-degree angle, so that will become transform. So to make the cis form, this CH3 group will be on the axial position. Similarly, the trans 1,4-dimethyl cyclohexane, as I said, in the case of this chair form, the most stable conformation of the cyclohexane is two CH3 groups at first and fourth positions. They are at the 180-degree angle, and that is why means both of them are at the equatorial positions. And these equatorial positions, usually also we know equatorial positions are less hindered positions. So this bulkier group will take the equatorial position. And in the form of this form, we show the trans isomer in this form. The CH3 group in this case is above, and in this case it is in this direction below this group. So this is trans 1,4-dimethyl cyclohexane. This one is cis 1,4-dimethyl cyclohexane. So this is name of this compound is cis 1,4-dimethyl cyclohexane, and name of this compound is trans 1,4-dimethyl cyclohexane. The geometrical isomers often show different physical and chemical properties. This is a very important point. The geometrical isomers, because they are isomers, it means they have different properties. That is why they are different, considered as different compounds. So they have they show different physical and chemical properties, and the difference in their physical and physical properties is more significant when there is more difference in their polarity. So what is this? This point tells that if the physical properties are different, more the difference is more when there is higher difference in the polarity of the two compounds. And the higher difference in polarity, if there is higher difference or greater difference in the polarity of the two compounds, then as we know, their physical properties will different. The polarity more polar compounds will have perhaps more association and maybe more dipole-dipole interactions, and because of more dipole-dipole interactions, they will have different uh, kind of crystallization, or maybe their packing will be stronger, and then the one is having. And this is not only the polar and non-polar form based on the simple thing, or based on the polarity, one can exactly say what will be the polarity or maybe the melting and boiling point of the two compounds. But based on this polarity, we can see there are much uh, things that one can play with. So the difference in this that physical property is more significant when there is more difference in their polarity. As usually we know the polarity for a compound, if the polarity is there, there are many things that is governed by this polarity, and this kind of things, examples we have already seen in chemical bonding chapter. You can just go and revise if you forgot. Usually the dipole moment of cis isomers is greater than that of the trans isomers. This is important point. The cis isomers have greater dipole than the trans isomers. Hence, the cis isomers usually have more solubility in porous solvents. So, any compound which is having higher dipole moment, it will be more soluble in polar solvents. That is very common thing that everyone understands. Other molecules having less dipole moment will be of very lower dipole moment, almost zero dipole moment will be more soluble in non-polar solvent. These kind of things, like dissolves, like polar solvent, polar molecule is molecules with having dipole moment. A non-polar solvent dissolves non-polar molecules, and non-polar molecules having very low dipole moment or maybe zero dipole moments. So let's see the example of cis and trans isomers. This is cis 1,2-dichloroethene. This is 1,2-dichloroethene. The two chlorine groups at two different carbon atoms at ethene. So 1,2-dichloroethene, and this can have two different isomers, symmetrical isomers. And the one is the cis form and another is trans form. If both the Cl groups are on the same side of the double bond, that will be the cis form. And if the two double bond, if these two different groups are on the opposite side of the double bond, then that will be the trans isomer. Let's understand one point. If by rotating this molecule, you may not get this molecule. Even suppose sometimes you just rotate a molecule and you get another structure, and these two structures were just which you obtain by the rotation only, rotation of the entire molecule, not one part with respect to other. The rotation of the entire molecule, then you can say this is the same molecule. It has just been rotated. The molecule has not changed its structure and its other properties are not changed. It has just been rotated. But if you are doing the rotation with respect to one part, one rotation of one part with respect to other part, then that kind of thing is different. Means you are twisting the molecule, and with the twisting of the molecules, you will get different structures. And if that structure, the new structure is stable, it means you have got a different isomer, and that is what we get in this case. If we keep this part fixed, and if you rotate this part with respect to the first part, suppose this part, this half is first and this part is second. So if you keep the first part fixed and the second part with respect to twist this molecule around this and give energy twisting with enough energy so that it can break the double bond, and then you get this one. So you can see this another structure, and after you get this molecule, the planarity you will obtain after the rotating around 180 degree, then again the pi bond will be formed because the p orbitals will be in the same position, same orientation, so they will overlap and you will get the trans isomer. So this is the trans isomers, you get another compound. And if you look at the polarity, this carbon and Cl, this bond is polar bond, this bond is also a polar bond. And the polar bond with respect to this polar bond, they have certain angle. Maybe you can consider 120-degree angle, this angle and this angle, 120-degree angle if you simply. So there is 120-degree angle between them, and the 120-degree angle and two vectors the same magnitude. So we will get the net magnitude certain magnitude, and if both the vectors have the same magnitude, so we will get the net resultant vector with the same magnitude, and that goes between. And this bond is also polar bond, so this polarity is around this. This is also polar bond, this, and this one is also polar. So this polarity is this, and this is this. So net dipole moment because of these two CH bonds, and net dipole moment because of these two CCl bonds, you will have certain dipole moments, and that is, it means it has non-zero dipole moment value in the cis form. However, if you look at the trans form of the same compound, it means trans 1,2-dichloroethane. So this is 1,2-dichloroethane, and the trans form, so the trans isomer. In this case, if you see this bond is almost 180 degree away opposite to this. This vector dipole moment vector is along this, and this dipole moment vector is along this. Both the dipole moment vectors are having same magnitude, but they are at the opposite angle. They are opposite to each other. Their orientation, they are opposing each other and having same magnitude. So net dipole moment here, they will cancel out the dipole moments of each other. Similarly, you see the dipole moment along this bond, the this dipole moment also along this bond, and these two dipole moments are bond moments are also opposite to each other and having same magnitude, so they will also cancel out each other. So there is a net zero dipole moment along for this bond, and because there is a net zero dipole moment for this bond, so the trans isomers usually you can say the zero dipole moment for this kind of compound trans 1 2 dichloroethene, and there is some dipole moments are having higher dipole moment value for this compound. Suppose if this was CH3 group, then this CH3 group, this sub bond moment will be, or maybe not, this is fluorine. So this fluorine will be having CLF and this is CCl. So they both will having some bond moments and they will be opposite to each other, though not same in the magnitude, but these two will be same in magnitude. They will cancel out, but you will get some dipole moments, but because of the opposite in their their opposite in direction, so very small value of the dipole moment in this case. So the trans isomers usually have very less dipole moment, and the cis isomers have greater dipole moment, and so cis isomers are more soluble in polar solvents than the trans isomers. Let's see another example of cis and trans isomers. Maleic acid is more acidic than fumaric acid due to intramolecular hydrogen bonding in the formed conjugate base. So what you see, this is maleic acid. Maleic acid, this is the cis form of this compound because two carboxylic acid groups are on the same side of the double bond. And so this they are the same side of the double bond. So this is cis form of this compound. Now this is the double bond and two carboxylic acid groups. This COOH group, this is also COOH groups. They are on the opposite side of the double bond. You can see this double bond like this, and they are opposite sides. So this is transform. So this is cis form, this is trans form. Both the acids are having different names, as you can see. This is maleic acid, this is fumaric acid. It means they are different acids. Are having different properties. And what are the different properties they possess? So first, let's see the lower melting point. This cis form is having lower melting and boiling points. And why they have lower melting and boiling points? And this trans form have higher melting and boiling points. And the higher melting and boiling points of the trans form is because this is more symmetrical structure. To look at the symmetry, this is more symmetrical than this. The more symmetrical trans isomer packs in tightly, and this one packs in tightly in the solid state. That is why it is having higher melting point. And even the liquid state, there will be more interaction between this transform because the packing and their orientation, they are larger inside there, and so this molecule will be bit spherical in size. This molecule will be bit linear in size. Because of the more linear structure, we will have more dispersion interaction, and more dispersion interaction. So this will be having more interaction, and so intermolecular interaction. Another region of intermolecular interaction will be this compound. It can have intramolecular hydrogen bonding. This compound maleic acid can have intramolecular hydrogen bonding, and if this OH group is involved in the intramolecular hydrogen bonding with this OH, so this compound will not interact with that much efficiency with another compound or another maleic acid compound. So the intermolecular interactions because of the intramolecular hydrogen bonding will also decrease because then the intermolecular interactions and the intermolecular hydrogen bonding. Intermolecular means the hydrogen bonding is hydrogen bonding between two different molecules. Intra means within the molecule. So we see intramolecular hydrogen bonding here more efficient intramolecular hydrogen bonding, and this compound we see more efficient intermolecular hydrogen bonding. And if there is a more efficient intermolecular hydrogen bonding, so the packing will also be more tight, more strong, and also the melting and boiling point will of this compound will be more. The trans isomers will be more than the cis isomer. So the fumaric acid is having higher melting and boiling points. This is more linear structure. This is more spherical structure. This is cis form and this trans form. Another property like that, if you look at the chemical properties, and the chemical properties, the maleic acid is more acidic than fumaric acid due to intramolecular hydrogen bonding, which is also called chelation. So like you see the maleic acid, and if the maleic acid, if one H plus group is removed, H plus, and that is what we call the Acidic property means that ability to furnish H plus or the proton with more ease, then you say such compound has more acidic compound, and it will depend on the stability of the conjugate base. And you see the conjugate base in this case, in the case of maleic acid, because of the chelation is more stable. This is positive charge, and because of the positive charge, this hydrogen bonding will get stronger. And this because of the stronger hydrogen bond, you see this kind of effect we call the chelation effect, and stable due to intramolecular hydrogen bonding. This is a maleic ion. In the fumarate ion, if suppose you remove H plus ion from one of the carboxylic acid group, then in such case, the fumarate ion this can also have hydrogen bonding, but this hydrogen bonding is not because of the same another carboxylic acid group of the same compound. It will form this hydrogen bond if the another compound is available in its vicinity, then it will form the hydrogen bonding. And because of this hydrogen, and we also saw this chelation effect. This chelation effect, the hydrogen bonding is stronger. In this case, even though hydrogen bonding is there, maybe the enthalpy will not matter that much, but the entropy factor will act here. And because two compounds are or two different molecules or two different ions are getting together forming one, so entropically it is not that favorable. However, in this case, the entropy will not matter. Only the thing will be the hydrogen bonding entropy, because these groups are already fixed or maybe in this orientation because of this they are part of the same molecule and they are rigid in their structure. Maybe this atom was freely, this hydrogen atom was free to move here and there, but other part is kind of already rigid in the part of the rigid structure, and so it is entropically more favorable. And that is why if the chelation is there, chelation is having uh, chelation is energetically more favorable case, means if there is intramolecular hydrogen bonding, molecules get more stability because of the intramolecular hydrogen bonding than in the case of intermolecular hydrogen bonding. Because in the case of intermolecular hydrogen bonding, we also know that adverse effect of entropy will come into play. And the adverse effect of entropy means that nature always wants to increase the entropy, and to increase the entropy means the less number of molecules to more number of molecules. Or if you go from more number of molecules to lesser number of molecules, you are creating order in the system, and creating order in the system is against the entropy, and so entropy will decrease. And any the free energy that we know, free energy, the spontaneity of any process is related is to it depends on the enthalpy change as well as change in the free energy. Delta G is equal to delta H minus T delta S. And so those things we have already seen in the thermodynamics chapter. Let's now see the conditions for geometrical isomerism. Means what are the conditions, what are the things when you see in a molecule and you can immediately say that, oh, this molecule shows will be having the geometrical isomerism. And so these are the conditions. First condition, these conditions briefly we have already explained. I have already explained that we will now see it in more details. There should be restricted, first condition is there should be restricted rotation somewhere in the molecule. And restricted rotation means what, in what form this restricted rotation will be there. We have to remember double bond or the ring structure. If there is a double bond or the ring structure, there will be a restricted rotation somewhere in the molecule. So if you look at this compound, there is a single bond between carbon-carbon atom, and because of this single bond, this molecule will, this part will freely rotate with respect to this part, and so there are free rotation about this single bond, and so they are different, although they have slight difference in energy, a little difference in energy, and also this barrier is not completely barrierless, but it is having very small barrier, so it is almost barrierless. So one can that barrier is easily surmountable at room temperature. So that is why we call the free rotation is about this double bond or the single bond. However, if there is a double bond, and if there is a double bond, we know there are 2 points of overlap in the double bond. One is below internuclear axis, another is above internuclear axis, and because of the 2 points of overlap is there. So if we want to rotate a particular compound with respect to this at 2 point rotations, you will have to break the double bond, or maybe that orientations of this p orbitals you are changing by because of the rotations. And if you are changing the orientation by rotation, it means you are breaking the pi bond. And so these are rotations. These rotations about a double bond is not free rotation. So in compounds with double bonds, the rigidity is due to the nature of pi bond or the p orbitals and their orientations in which they overlap. And in the cyclic compounds, the rigidity is due to the cyclic structure. For example, this compound, you know, this compound there are two single bonds between this group and this group. So this group are these two carbon atoms are connected with each other through two different set of double bonds. And if you want to freely rotate this, you have to break this bond or maybe one bond and another, then you can rotate only. So there is, if you want to rotate this part with respect to this part, so this rotation will not be easy because there are two bonds that is are there here in this compound. So this is the same compound in this compound. Another isomer, the similar thing you will say. If you want to rotate this part with respect to this part, then we'll have to break some of these bonds. So similar things we see there. So in the even in the ring structure, we see this kind of rigidity is there. Now the second criteria is the groups attached to the carbon atoms around which the rotation is restricted should be different. So first criteria is there should be restricted rotation. Even if there is restricted rotation, it doesn't mean this compound will necessarily show the geometrical isomerism. Why not? So let's see. If the two groups, suppose one with one carbon atom, the two groups which are attached to a particular carbon atoms are same, then you cannot such compounds do not show geometrical isomerism. And why? Because you can see this molecule and this molecule. If I just rotate this molecule along this direction, I can get this molecule, and rotating this molecule, I get the same molecule. It means the two molecules are same; they are not isomers because by rotation the molecule is same. We have just rotated the entire molecule, not one part with respect to another part. So you can get this molecule from this molecule simply by rotating it, the entire molecule, and so this is so the two swiping the right hand group, this right hand groups around still gives the same molecule. Simply turning the whole model over will give the other structure of the molecule. It just means that simply turn the whole model over, this you will get this, or you just rotate this along this, you will get this molecule. So we won't have geometrical isomers if the same groups are attached to any side of the bond having hindered rotation. So if the any side of the bond having same groups which is having hindered rotation and the same groups are attached to it, then such molecules do not show geometrical isomerism. Suppose this group also has the same pink group, then this will also not show the geometrical isomer. All the groups are same, four groups are two different carbon atoms. Or even if these two different groups are different and on this carbon the two groups are same, then it will also not show the geometrical isomerism. And there must be two different groups on the left hand carbon and two different groups on the right hand one to show the geometrical isomerism. And as you can see here, so two different groups at this carbon atom, two different groups, this blue group and the pink group, and this carbon also two different groups are there, blue group and the pink group. Now if you rotate this molecule, now if by any rotation in any direction at any angle, you will not get this molecule. By entire rotating entire molecule, you will not get this molecule, or by rotating this entire molecule, you will not never reach to this molecule. You can reach to this molecule from this molecule only when you rotate this part of the molecule with respect to this, then only you will get, and this rotation should be around 180 degree rotation. So this part, so if I rotate this part of the molecule with respect to this, I mean twist it with so much energy, then only I will get this structure. So these two are geometrical isomers. First of all, they are hindered. There is a hindered rotation between two carbon-carbon bonds, and then these two different groups are attached to each of the carbon, which are part of the hindered rotation. So this carbon is also having different group. This carbon is also having different groups, and these are the two isomers. So the two same groups are on the same. So this is cis isomer. This is trans isomer. Now let's see if the anyway the two different groups and only two groups are attached here. The similar examples you can see in this case, hydrogen and chlorine at both the carbon atoms. So they are cis and trans isomers. So here hydrogen and methyl groups, the same group, hydrogen carboxylic group. So they are cis trans isomers, but one can have three different groups attached to. So this is one pink group attached to this carbon and one green group is attached to this carbon, and another to another carbon, another blue group and the pink groups are attached. So this will also show the geometrical isomerism because there is a hindered rotation and each carbon is associated to two different groups, and this group and this group. And what is the related, or maybe the relative change in orientation means in this molecule, this methyl is oriented, this not on hydrogen one can say, or maybe the pink group is has come to in this orientation, and yellow group has come in this orientation. Sorry, blue group, and in this one, the blue group is like this, and pink group in this orientation. However, in this compound, two pink groups, this pink group is in this direction, so it is same. This one is also same, but what we see the difference is that this carbon atom, the pink one is along this one at the orientation of the blue one, and the blue one is at the orientation of the pink one, which was in this compound. So the orientation is different. The bonding, the chemical bonding is same. So this is what the definition we have already seen. Same constitution and a sequence of covalent bonds. So we see the same constitution and the sequence of of the covalent bond. This is single bond, this is double bond, single bond, double bond, single bond, single bond. Here also single, single, double, single, single. So same constitution of double bonds and orientation of double and single bonds are there, or the covalent bonds are there. Only the difference in the groups, different groups that are linked to this or the orientation of these groups. Now this group is having two different groups, the blue and the pink one. Let's see this example. This is also having two different groups, pink one and the green one. So this will also show geometrical isomerism, and geometrical isomerism is you just rotate this part with respect to this, or maybe you can just change these two groups, bring this group attack, connect this group to this in this orientation or this position and this one in this orientation. So you will get this as also cis isomer. This one can called trans isomer because these two groups are same on the same side of the double bond. So this is cis isomer, this is trans isomer. Another way to show the isomerism is suppose this is what we call the pink blue, pink pink, pink pink, pink blue. So what do we see? We do not see any difference. Pink blue and pink pink, pink pink, pink blue is the same in both the cases. However, in this case, if you look at here, pink blue, blue pink, the orientation, this order is pink blue, blue pink. Here, pink pink, blue blue. You can see the pink pink interaction, pink pink, blue blue, pink blue, blue pink. So this is different. So they are isomers. So this will show the isomerism. This will not show isomerism because the same orientation, pink blue, pink pink, pink pink, pink blue. We see the same kind of arrangement there. But do not show geometrical isomerism. In this case, you see pink blue, green pink, pink pink, green blue. So different orientations, different order, different permutations we are getting, and so they are geometrical isomers. And even if all the four groups that are connected to these two double bonds are different, then we also see the geometrical isomerism. So this is pink, green attached to this carbon atom, this is orange and blue attached to this carbon atom. And so the geometrical isomer of this will be just change the orientation of these two groups, or maybe keep this one fixed and change this one. So we can have the same thing. So it can have the three different isomers. So this one is what? Pink, blue, green, orange. This is pink, orange, green, blue. And if I rotate this one, I have rotated with respect to this. Suppose I keep this one fixed and rotate this one. So green, orange, and pink, blue. That is same as this one, and so that is not a different isomer. It will be just having the same isomerism. So now what we know, this type of isomers, if such kind of compounds are there, means all the four different groups are attached to the double bond, then we cannot represent this compound for these isomers as cis or trans. You cannot say anyone as cis and trans because cis means two same groups are connected to the same side of the double bond and there are no same groups at any side. So one cannot use E and Z notation for such compounds, and what kind of notations will use to represent such compounds and to represent to give a unique notation for such compounds or all kind of compounds people had derived this EZ notation, and EZ notations, that is what we require. So the simple convention of denoting the geometrical isomers by cis trans notations is insufficient, and that we see here in this case when there are more than two different substituents on a double bond. So more than two different substituents are on the double bond, the four different substituents are on the double bond, then we see this cis trans isomerism. This kind of notations are not sufficient. Up to the three groups you may use, and cis and trans isomerism one can represent, and one can uniquely write the structure. But in this case, all the four groups are different. One cannot use cis and trans notations to represent different geometrical isomers. So we need a special kind of notation, and that is EZ notation, a different notation, a specific notation, a different kind of notation, and that is what we call the EZ notations, a new nomenclature system for such compounds having more than three different groups or more than two different groups. So means three or four groups are different. So a let me again explain this. The simple convention of denoting the geometrical isomers by cis transmutation is insufficient when there are more than two different substituents on a double bond. A new nomenclature system known as EZ notation method is adopted to differentiate the stereochemistry in them. So for differentiate to denote the stereochemistry in these two compounds, we need to resort to EZ notation. So according to this approach, if the groups with higher priorities are present on the opposite side, this is what I have already said in this case, higher priorities on the same side, then such notations or such isomers or such geometrical isomers are called Z isomer. This is what we have seen. So according to this approach, EZ approach, if the groups with higher priorities are present on the opposite side, on the same side of the double bond, that isomer is denoted by Z. And the G, and where G means Susamen. And the Susamen, this is pronounced as Susamen, this is a German word, and it is pronounced as the Susamen. Though it is written as Josamen, but it is pronounced as Susamen. So J means Susamen, it means together. Means the two same groups are groups with the same priority are together or on the same side. It means this is a Z notation. Now, if the groups with higher priorities are present on the opposite sides of the double bond, then that isomer is denoted by E. And the E notation we have already seen in this example. Higher priority groups on the opposite side. They are opposite sides, so this is E isomer. And so this E means Entgegen. This is pronounced as Entgegen, and this Entgegen, though it is written Entgegen, this is also a German word which means opposite. Entgegen, E means opposite, and if the higher priority groups are on the opposite side, higher priority, suppose these two bulkier groups are higher priority groups, so they are on opposite side, then this is E notation. And this is the Z notation. The higher priority groups or bulkier groups are on the same side, so one can just say this is G notation. And this is pronounced as Entgegen. So in writing IUPAC name, the letters E and Z are represented within parentheses. This is what I have said earlier to you. So these notations E and Z are represented within the parentheses in writing IUPAC name of the compound with this isomerism, and are separated from rest of the name with hyphen. And so this E and Z should also they should be in parentheses, and they should be separated with or named rest part of the names with a hyphen. And these examples we will see later on. Like here you see in this example, we have used hyphen, but we forgot to put a parenthesis here. So we forgot to put a parenthesis. There should be parenthesis. The hyphen is already there. Now let's see the procedure to determine but what means the higher priority groups and the lower priority groups we have talked about, I have talked about, and does it mean higher priority groups and the lower priority groups? How will you determine which group is having higher priority and which group is having lower priority? One thing I have said, if the bulkier group is there, usually it will get higher priority, but that is not necessarily, that doesn't necessarily means it will hold true in all the cases. So there is a certain procedure, there is certain rules that we have to follow, and that rule is called Kahn involved Prelog sequence rule or CAN rule, and which we'll study it later. So the procedure to determine the EZ configuration. Let's see, first determine the higher priority group on each end of the double bond. So there are two ends of the double bond, and each end you will have to find out which group is having higher priority. So at the both ends of the double bond. And once you are able to determine the groups with the higher priority, then it becomes easier to write E and Z notations, because if the higher priority groups are on the same side, then it is a Z notation, and if the higher priority groups are on the opposite side, it means the E notation, and Z means, we know Z means together and E means opposite. And J, it, it stands for zusammen, and zusammen means together. Zusammen is a German word, and E represents entgegen, and entgegen means opposite. So also a German word. So if they are they are on the same side, this descriptor must be used. The priorities are assigned by following Kahn-Ingold pre-log sequence rule, and this Kahn-Ingold pre-log sequence rule is described here. So rank the atoms directly attached to the olefinic carbon according to their atomic number. So all the groups that are connected to the olefinic carbon and the carbon having the double bond, to rank them directly according to their atomic number, and high priority is given to the atom having higher atomic number. So this is simple. If the two different groups are there, like we have seen in the case of fluorine and chlorine, as I said earlier, this fluorine and bromine. This group is having higher atomic number, so this will get higher priority than this. And the directly atom, and this example, this carbon atom is directly linked to this carbon, olefinic carbon. So this carbon is having the atomic number 6 and the hydrogen having atomic number 1, and so this is higher priority group. This is having higher atomic number. Bromine 35, this fluorine 9, atomic number 35 9. So this is higher priority group. So based on that, this priority is determined here in this simple example. Now let's see another rule. If the isotopes of the same elements are present, because sometimes of in the kinetic isotope studies we also use isotopes, and if the isotopes are there, then the higher priority will be given to the heavier isotope. And so the higher priority is given to the isotope with the higher atomic mass, the heavier isotope. So if we suppose the example, if the deuterium and hydrogen are attached to the same carbon atom, same olefinic carbon atom, then in that case as well we'll see the geometrical isomers. Even if the isotopes are there, then will geometrical isomers, they are not same groups. Although they are having same number of number of protons in their nucleus, but they are different groups, they are having different size. And so the higher isotope will be given higher priority. So if some hydrogen and deuteriums are attached to the hydrogen and deuterium are attached to the same olefinic carbon atom, then deuterium will be given higher priority than the hydrogen atom, or that the hydrogen is for the protium. Protium is the one hydrogen one isotope. Deuterium is hydrogen two isotope. So similarly, if the carbon 13 and carbon 12 isotopes are connected, so the carbon 13 would be given higher priority or more priority over carbon 12. Even the isotope of phosphorus 31 and 30. So phosphorus 31 will be given more priority over the phosphorus 31. All kind of examples you can see. So if one can combine the rules for 1 and 2 and give one rule, means the atoms with the higher molecular weight or the higher mass number, a higher atomic mass should be given higher priority. The higher atomic mass, any that usually, but that is not necessarily, because we also see there are isobars. And the case of isobars, we will have the confusion. So if there are isobars, then the atomic number preference will be getting the, so these rules will be acting there. So the first is what the atomic number, higher atomic number. If the two atoms connected to the olefinic carbon have the same atomic number, it means they are isotopes, then we will see the mass number or atomic mass, the heavier one will be given higher priority. The rule number 3 tells if the atoms are still identical at the first carbon atom, if you don't see any, the first atom which is attached to the olefinic carbon atom, there are examples when you don't see any difference at the first atom. Like suppose a olefinic carbon at one side, the CH3 group is attached, and another side the C2H5 group is attached. At the first carbon atom, we will see both the compounds, the carbon atoms, only the carbon atoms are attached, so we cannot see the difference at the first carbon atom. So if the atoms are still identical, examine the next atom along the chain. So if the first carbon is same, then examine the second carbon or second atom at L, which is attached along the chain. Then the third atom and the fourth atom, and still you don't see any difference, then you go further. And so examine the next atom along the chain until a first point of difference is found. And you keep doing this until you see a first point of difference. And as soon as you get a first point of difference, you should just stop there and give the priority to different groups. So this is done by making a list of atoms linked directly to the first atom. And so what will so we'll link all the atoms which are list all the atoms which are linked to the first atom, and each list is arranged in order of decreasing atomic number, and then all the groups which are attached atoms are attached, you can write them in the decreasing atomic number in this order, and then you can see at what order at which place there is a difference you see, and you see the difference at a particular period, then you can give the priority to different groups. Then the higher priority is given to the list which contain atom with higher atomic number at first point of difference. And this means that let's see this example. If this compound is there, and in this compound you see this is a double bond, this is the olefinic carbon, this is olefinic carbon, this carbon part of the double bond. Then you see at the first point of difference, at the first point of linking, you won't see any difference. All are carbon atoms denoted with a star. Now then we move to the second carbon atom along the chain until we don't get any difference. And so this and this at this carbon atom we'll see the olefinic carbon atom two groups CH2OH, and the CCH3 thrice group is attached. So at this carbon atom, what are the different atoms which are linked to this carbon atom? Carbon, carbon, carbon. You can see this carbon, this carbon, and this carbon. Three different carbon atoms are connected. Here to this carbon atom, one oxygen and two hydrogen atoms are connected. So oxygen will be written first in this order, and then two hydrogen atoms. Now let's compare this. See, the atomic number of this oxygen at the first point is more than the atomic number of this carbon atom, and that is why this one will be given higher priority over this. So this is what will be given higher priority, high priority of priority 1, and this will be given priority to this carbon atom. So maybe this group will be given second priority. And if you look at this carbon atom, this olefinic carbon, two groups are attached here as well. So now this carbon atom at the first point we won't see any difference. Both are carbon atoms. Then we see this carbon atom is linked to one carbon atom, then two hydrogen atoms. So carbon atom will light first because its atomic number is more than two hydrogen atoms. In this case, this carbon is attached to three hydrogen atoms. All the hydrogen atoms are here. All the atoms are hydrogens. So now we see the difference. This at first position itself we see the difference. So this will be given higher priority. So this group will be given higher priority. This is one and this two, and the same higher priority groups are on the same side, and so this will be the Z isomer of this compound. And so in this case, you can also see this is 2Z. And why this is represented as 2Z? Because in the IUPAC nomenclature, you have to find out the number, give the numbering. And the numbering means the numbering will start from this. This is a functional group, so will numbering will start from this carbon 1, 2, 3, and this main chain also should consider the should contain the double bond 3, 4, and 5. So this is 1, 2, 3, 4, and 5. So anyway, so this is 5 carbon atoms, and this is at the 2Z position. So there is some error in this the name of this compound. So I'll correct it later on. So anyway, you should also say this. No, no, there is no error. This is butyl. This is tertiary butyl. This is absolutely correct. And this is pentyl. I forgot. I thought this is butane. So this is 2Z at the second position. Z isomer is there. Z symmetrical isomerism is there. So this we represent 2Z in parenthesis, then hyphen. Then this group will behave as a substituent of the branch, and this will also behave as a branch. So this is tertiary butyl and this is methyl. So butyl comes first, so then the IUPAC nomenclature this will be written first. So 2 tertiary butyl, then 3 methyl, pent 2 in 1 all. Pent 2 in 1 2 and 1 all is the IUPAC name of this compound. Now let's see another rule which is also very important. The multiple bonds are counted as multiples of that same atom. So multiple bonds are counted as what? The multiple of the same atom. Suppose there is a double bond, carbon, oxygen, double bond. It means it that a carbon is associated to two oxygen atoms. So this carbon and two oxygen atoms are there. So this is how we decide the priority. The multiple bonds are counted as multiples of that same atom. That is, each pi bond is treated as if it were another sigma bond to the same type of atoms. And this is how, so if you look at the example, the C triple bond CCH3. C triple bond CCH3 will be treated as, means this is equivalent to this C, this is a star, the first carbon atom. Then this, there is a triple bond, it means this carbon is connected to three carbon atoms. So one carbon atom here, this one, and this is connected to CH3, and this carbon atom now is connected to another carbon atom. This is how it is interpreted. And this carbon is also associated to three different carbon atoms. One bonding we have already seen, shown, the another carbon and another carbon. And this is how we compare to give the numbering. Now this C double bond OCH3 is equivalent to this. This is carbon, the star one, and this oxygen. There is two carbon oxygen bonds. So one carbon oxygen bond is this, and and another carbon oxygen bond is this. And one of this we also see there are two oxygen carbon bond. One oxygen carbon bond is here, another oxygen carbon bond one can treat here, if not here, here as well. And this group is attached to the CH3 group, so CH3 group is here. So what we see, we break the double bond or multiple bond and multiply it with the similar number of groups, and this is how then we get the priority. So let's see the express the cis and trans to butene in EZ rotations. So this cis and trans butene, let's this question in, we have to represent it in the EZ notations. So now let's see this cis 2 butene and this is trans 2 butene, the structures that you already know, we have already seen. Now the priority will be given this atom. This is carbon, this is hydrogen. So this one will get first priority one, first priority, this will get second. And here also this one will get first and this one will get second. The higher priority, lower priority, higher priority, lower priority. And the higher priority groups are on the same side of the double bond. So this is Z notation. So this form the will be the Z form. And the IUPAC name of this compound will be 2Z, second group, the carbon atom, the Z notations we see. So 2Z 2 butene. Now this one, this is will get carbon atom, atomic number 6. This is hydrogen atom, atomic number 1. So this one higher priority, this one lower priority. Now this olefinic carbon, this group and this groups are attached, these two groups, and this group 6 atomic number 6, and this one is having atomic number 1. So this will get higher priority, this lower priority, higher priority groups on the opposite side. So this will be E isomer. And the E isomer again will be at the second carbon atom which is start. So this is 2E 2 butene. So these are two different compounds. One can also represent with the name. So this is cis 2 butene. Either you can write cis 2 butene or trans 2 butene or 2Z 2 butene or 2E 2 butene. And as you can see, 2Z and 2E are written in parentheses, and after that we have written a hyphen to connect with rest part of the name of this compound. And similar thing we have done for this compound as well. As the double bond is at the second carbon of the butene, as you see, the number 2 is used before the descriptor Z or E, and so this is what we write 2Z and 2E. Let's see this question. Write all the possible geometrical isomers for the compound 3-methyl hexa 2,4-diene. So this is 3-methyl hexa 2,4-diene. So 6 carbon atoms are part of the main chain. So we'll write 6 carbon atoms. Then we'll have 2 double bonds at the second and fourth position. So first, second position and the fourth position, and the 3-methyl as a substituent and the third methyl. This 1, 2, 3. So at the substituent we have written. Now this compound can have how many? It can have 4 geometrical isomers, and one is at this portion. This is geometrical isomer. It will show geometrical isomer because this is in the rotation around this double bond, and this double bond is having two this carbonate olefinic carbon is attached to two different groups. One is hydrogen and one is methyl. Here this is also connected to two different groups. This is methyl and this is this one group. So there are two isomers here at this position, and another two isomers will be at this position because this is also a stereogenic center or the geometrical center. The stereogenic center or geometrical center means this is also, this is hydrogen and this is another bulkier group, and this is hydrogen, this is methyl. So this is also a stereogenic center now. So we can have total 4. So 2 into 2, 4 combinations will be there, 4 different geometrical isomers. So this compound can have 4 different geometrical isomers. So there Means this name, a compound with this name of this molecular formula can have four geometrical isomers. So one can have four different compounds with the same molecular formula. Now this form is what? Let's see, this form is this is higher priority group, this is hydrogen lower priority group. This one is higher priority group, this one is lower priority group. So this will become E. Why this one is higher priority group? Because this is the polyphenic carbon and CH3 group, and then carbon, hydrogen. Here what we see, carbon and carbon double bond. Carbon double bond is carbon we will have to write then hydrogen. So carbon, hydrogen. At the second position we see the difference. This is CHH, this is CCH. So we see at the second position difference. So this will be given higher priority, and so the higher priority groups on the opposite side. So this is E form. Now if you look at this form, if you look at this form, this is the higher priority group. As you know, this is the carbon and there will be hydrogen. So higher priority, lower priority. This is higher priority. This is the lower priority hydrogen. So the this will also be E group. So higher priority groups are opposite side. So this is also E isomer. So this one can write the name of this compound as 2E and 4E, then 3-methyl hexa 2,4-diene. This is 2E 4E isomer of 3-methyl hexa 2,4-diene. Now, if you change the stereocenter at this position, the stereochemistry, if you change the stereochemistry at this position, so what we will do is just bring this group at this side and hydrogen bring opposite side. So hydrogen is here. This thing we have kept same. So hydrogen is here. Now the priority high priority group here on this olefinic carbon on the at this side, and at this carbon it is still on this side. So the higher priority groups are on the same side. So this will become at the second position. It will become at the second position. It will become Z. So this is Z isomer. So this will become 2Z and this is still 4E. We have not changed this one. So 2Z 4E 3-methyl hexa 2,4-diene. Now if you keep this one same and make the changes at this position. If you make the changes at this position, so this was initially E, you make it Z, so you bring this group at this side and H in this orientation. Now the methyl is in this orientation and hydrogen in this orientation. This methyl higher priority group and this higher priority groups are the same, and the same means this will be Z, and this one like this one will still be E because this is higher priority and this one is higher priority opposite side. So this is 2E4Z 3-methyl hexa 2,4-diene. Now if you look at this isomer, so this one is here and this also we have changed. This was E. Now we can bring this group down to make it Z as well. So this is becomes 2Z 4Z 3-methyl hexa 2,4-diene. So one can have four isomers are all combinations. EE, EZ, you see EE, ZE, EZ, ZZ. Four combination EE, EZ, ZE, ZZ. Four combinations. So four different isomers are possible here in this case. So note that descriptor cis, trans, E, Z, etc. are used only when the double bond possesses geometrical isomers. If the double bond do not possess geometrical isomers, suppose this group was hydrogen, and if this was hydrogen, this double bond will not possess a geometrical isomer. So we won't show for this double bond any Z or E isomerism. Or when the C is trans, we cannot say for this one. I mean the fourth carbon at the fourth carbon atom. Now let's see the EZ notations of the enzymes. This will be the last point for this class, last topic for this class. So the enzymes are, as we know, we have seen the examples of enzyme nitroso and enzyme tautomerism. Earlier, we are familiar with this term enzyme. So the enzymes are formed when carbonyl compounds, which carbonyl compounds are aldehydes or ketones, are treated with hydroxylamine. Hydroxylamine is what? NH2OH. NH2OH is hydroxylamine. When these aldehydes are treated with NH2OH, we see the formation of enzymes. And if the carbonyl compound was aldehyde, then we can call such enzyme as aldoxyme. If the carbonyl compound was ketone, then we can call such enzymes as ketoxyme. So there are two different types of enzymes. The aldoxyme, these are derived from aldehydes, and ketoxymes are derived from ketones. So you can see here this aldoxyme means one, this was carbonyl group and this is NH2OH, this carbonyl group C double bond O, and this is aldehyde, one alkyl, one hydrogen group. And here in this case of ketones, both the groups are alkyl groups, and you can see here R and R are R and R primes are alkyl or aryl groups. This is ketoxime. So this ketoxime, aldoxymes also show geometrical isomerism, and geometrical isomerism they show also because they also have lone pairs. So this nitrogen has a lone pair of electron. This also has a lone pair of electron, and you can see here. So the Z oxime, so Z oxime has the hydroxyl group and the group with the higher purity on the same side. So this is what we call the hydroxyl group. This oximes is also considered, always considered to be group with the higher purity. And this carbon center, we see the higher purity will be given to this one, and the lower purity will be given to this one. The higher purity methyl group on the in this side, and OH with the higher purity group on this side. They are opposite side. So this one is E isomer. So this is one E N hydroxyl ethanamine, ethenamine. So this is double bond N group is called imine, and double bond N group is called imine, and this nitrogen OH group is attached to the hydroxyl group is attached to nitrogen. So we call this N hydroxyl, and at first position this N hydroxyl 1E is attached. So 1E N hydroxyl, because this is the carbon atom 1 and 2, the numbering will start from here and it will go here. So to get the longest carbon chain, and this is N group, so N hydroxy 1E, and this is E because of this, and 1E N hydroxyl ethane. This is ethane, but this is what? This is not amine. This is imine, double bond, carbon double bond Na. So this is imine, one ethena imine. Ethenamine is what we write here. And this is what the Z form. This is the bulkier group on this part, or the heavier group, or the more purity group, carbon and hydrogen. And this is OH group. It is always considered to be higher purity group with respect to the lone pair. So the higher purity groups on the same side and higher purity groups on the same side. So this will become Z isomer. Now the numbering will do 1 and 2. The numbering is same as we saw for this case. So then 1, 2, this is also N 1 Z, 1, this is Z isomer, and this means OH and CH3 groups are on the same side, it will tell Z form. So 1 Z, N hydroxyl, ethane, imine. So N hydroxyl, ethane, this for ethane, and this is for imine. So we see when this the Z oximes has the hydroxyl groups and the group with higher purity on the same side of carbon double one nitrogen, whereas they are on opposite sides of the E oxime. So in E oximes, they are on the opposite side. This is the E oxime, and this higher purity group and the OH group hydroxyl groups are on the opposite side, and the Z oxime higher purity group on the carbon and the hydroxyl groups are on the same side. So sine and anti notations are also used to represent geometrical isomers. This we are not going to study. This is not that much important. The EZ notations you should remember. EZ notations and cis and trans isomerism. You should also note that because of the lone pair hydroxyl amines or amines, or not amines, hydroxyl amines also show geometrical isomerism. And what are the hydroxyl amines? Hydroxyl amines are compounds, a chemical compound which are formed because of the reaction of carbonyl compounds. Sorry, these are aldoxymes or ketoxymes. So these are oxymes. Simply the oxymes are formed because when the carbonyl compounds react with the hydroxylamine means OH NH2. So you know hydroxyl group is OH group and amine group is NH2 group, and so there is a O and N bond, ON linking. So OH single bond NH2 is hydroxylamine. So if the any carbonyl group react of any compound with the carbonyl group react with hydroxylamine, actually these two hydrogens of the amine will react with the oxygen of the carbonyl group or the ketones or aldehyde, and the water molecule will be produced as a side product, and the aldoxyme or the ketoxymes will be formed accordingly as the main product. So those are called oxymes in short, and oxymes can be aldoxymes and ketoxymes that we have already seen. I'll stop this lecture at this point, and we'll see the optical isomerism in our next class. I hope you enjoyed this lecture.